Right. Looks like today we're going to do lecture 9, 28, and 29, OAS A2A14 is our standard. The student will factor a difference of squares, first factoring out the greatest common factor if necessary. Okay. So before we get started, I just want to talk about what a difference of squares is. A difference of squares is simply a difference of two values that are being multiplied by themselves. It could be any two values. It doesn't have to be an A and a B. If something is being multiplied by itself minus something else that's being multiplied by itself, which is what the second power means, you multiply the base by itself, this is called a difference of squares. And when we go to factor those, and that means to break it up into two things such that if you multiply them together, you get what you started with. For instance, if I said to factor the number 6, you would tell me, well, we could go 1 times 6. Or you could tell me, well, we could go 2 times 3. In either case, I would have factored 6. Here are 2 factors of 6. Here are 2 more factors of 6. We've broken it up into 2 numbers such that if I multiply these two together, I get this. And that's what we're going to be doing with the difference of squares. If we know that a binomial is a difference of 2 perfect squares, those are 2 things that are actually being multiplied by themselves, then that means A times A and B times B. Then we can factor it using this pattern. Put the square root of this one, the square root of A squared is A, here and here. Put the square root of this one, the square root of B squared is B. Put that here and here. And put a plus sign in between these two and a minus sign in between those two. And if you FOIL these, you'll get this. The middle terms will always subtract out, okay? And you'll see what that means here in just a second. Let's take a look at this. I'm going to use this pattern to factor difference of squares. This is factor. Always check for a greatest common factor. Well, that means you're asking yourself, do these two terms have any factors in common? For instance, could I divide both of them by 4? Well, that won't divide by 4 evenly. Neither one of them have a common factor, so I'm just going to go straight into this pattern right here. A difference of 2 perfect squares. That's k times k, that's 2 times 2. Okay, it doesn't have a little square above it, but I know that 2 times 2 is 4. So that's a perfect square, that's a perfect square. This is a difference. That's what difference means, subtracted. The difference of 2 perfect squares. So I'm going to use the pattern. I'm going to open up 2 sets of parentheses. I'm going to take the square root of this one, the square root of k squared is k, and put it here and here. I'm going to take the square root of this one, and square root of 4 is 2. I'm going to put that here and here. And then I'm going to make one positive and one negative, just like I did up here in the very definition of a difference of squares, okay? So what I said earlier was that if I multiply these 2 things together, I'll get this. Now this is my answer. I'm going to multiply these 2 things together just to demonstrate that this times this does indeed equal this, okay? But this is the answer I'm looking for when I'm asked to factor. I'm going to go ahead and demonstrate that this times this is indeed k squared minus 4. So here we go. I'm going to take this k. I'm going to distribute it. That gives me k times k is k squared. K times negative 2 is negative 2k. Then I'm going to take my second term and distribute it. Distributing positive 2. I won't do this every single problem, I just wanted to demonstrate. 2 times k is plus 2k. And 2 times negative 2 is negative 4. Now when I go to combine these like terms, you'll see that these 2 middle terms are going to cancel each other out. And that will happen every single time if you multiply k plus 2 times k minus 2, or in general, a plus b times a minus b, where a and b can be anything, as long as it's something plus something and the same thing minus that other thing. If it's that pattern, you'll always wind up with a perfect difference of squares if you multiply them. That means if you factor a difference of squares, you'll wind up with those 2 factors. So I just demonstrated that I can factor this into this, and I demonstrated that if I do multiply these 2 things together, I wind up with, because these cancel each other out, 2k minus 2k is 0, I'm up with k squared minus 4. So if I do multiply these two things together, I wind up getting k minus 4. Now back to what I was saying earlier, this is the response we're looking for. I was just demonstrating that if this times this, if these are factors of k squared minus 4, then this times this should equal k squared minus 4, and it does, okay? And I won't be demonstrating that anymore. But I will be doing the rest of them using the pattern above. I recognize this as two perfect squares, something squared minus something squared. Squared means multiplied by itself. I see that this is 4x times 4x, and this is 3 times 3. So this is a difference of two perfect squares. They don't have any common factors that I can pull out. This won't divide by 2 or 4. This won't divide by 3. So there are no common factors I could factor out. So I'm going to go straight into my pattern. This is a difference of two perfect squares. I'm going to open up two sets of parentheses. I'm going to take the square root of this one and put it here and here. Well, that's the thing that I would multiply by itself to give me 16x squared, and that would be 4x. 4x times 4x is 16x squared. It has to be multiplied by itself. These have got to be the same term. And then I'm going to take the square root, so to speak, of 9 and put it here and here. And I put a plus sign here and a minus sign there, and I'm done. That's this. If I'm asked to factor it, because it is a difference of two squares, we'll factor using this pattern right here. The square root of this one here and here, the square root of this one here and here, plus minus. That's exactly what I did here. The square root of 16x squared is 4x. I'll put that here and here. Square root of 9 is 3 here and here, plus minus. And there's our factored difference of two perfect squares. Okay, let's do another one. I look here, they don't have any common factors, so I'm just going to go right into my pattern. The square root of 9x squared is 3x, because 3x times 3x is 9x squared. So I put the square root of the first one here and here. I put the square root of the second one. 4 times 4 is 16. Here and here. Make one positive, one negative, and I've got it factored. 3x times 4 times the quantity 3x minus 4 will equal 9x squared minus 16. The middle two terms will cancel out just like they did here when I demonstrated that. Okay. And here we have another one. This is 25k squared minus 1 is a perfect square. That's 1 times 1. It doesn't look like it has a square there, but it's still a perfect square. 1 times 1 is 1. So I'm going to use the the difference of squares pattern. I take the square root of this one. Well, 5k times 5k is 25k squared. So I'm going to put 5k here and 5k here. I take the square root of 1 and I put it here and here. Well, the square root of 1 is 1 because 1 times 1 is 1. Then I make one of them plus, the other one minus, and I'm done. I factored it. Okay. So here are 4 examples of factoring, just a difference of squares that don't have a common factor to factor out first. I looked, and every time I didn't see a common factor, so I didn't bother with it. However, on these next ones, remember, we always factor out the greatest common factor if we can find one, if we can see it. Okay, and I look up here and say, well, these are both divisible by 3. So I'm going to factor out a 3. That means I'm going to write a 3 and open a parenthesis and ask myself, what would be left if I took the 3 out of this? In my head, I'm dividing it by 3. Well, that would leave me with n squared. If I took a 3 out of this, now I'm dividing it. When I pull it out, when I'm writing it and pulling it out, I'm dividing that by 3, and that would be 16. And I can do a quick check to see if I've factored out my common factor correctly by just in my head multiplying this and seeing if I get that. And I do. 3n squared minus 48. Now I look at this and I say, hey, that's a difference of two perfect squares. That's n times n, that's 4 times 4. So I'm going to leave this 3 where it is. It doesn't disappear. I'm going to bring it down in my next step. It's outside the parentheses. And I'm going to factor this using my pattern, a squared plus b squared. We'll take the square root of this one, put it here and here, square root of this one, put it here and here, 1 plus sign, 1 minus sign. That's the pattern. And I see this is a difference of squares, so I take the square root of n squared, which is n. I take the square root of 16, which is 4. Make one positive, one negative, and there's my answer. I had to factor out the greatest common factor first. That was the biggest factor that they both had. I saw that they both divided by 3, so I pulled it out. And I said, hey, this is a difference of perfect squares. So I rewrote my 3 and factored this into a difference of squares. I'm going to do the same thing here if I can. The first thing I see is that these will both divide by 5. So I'm going to pull that 5 out. I'm going to factor that 5 out, just like I did with this 3. Okay, so I see that they're both divisible by 5, so I call this 5. If I pull a 5 out of this, you're dividing when you pull it out. That leaves me with 9p squared, because 5 times 9p squared is 45p squared. Minus, if I pull a 5 out of this, that's a 1. Because when you're pulling it out, you're dividing it. 5 divided by 5 is 1. And I see that this is now a difference of perfect squares. This is 3p times 3p, and this is 1 times 1. A perfect square is something that is yielded by multiplying something by itself. So that's a perfect square, and so is that. I'm going to factor it using the difference of squares pattern. My 5 is going to come down. I'm going to open up 2 sets of parentheses. Take the square root of this one, that's 3p, because 3p times 3p is 9p squared. And I'm going to take the square root of this one. Put it here and here, make one positive, one negative, and I'm done. First I factored out the greatest common factor, which was a 5 in this case. And then I said, hey, that's a difference of squares also. So I factored it using the difference of squares pattern. Okay. And the last one, well, I got 2 more. All right, yay. I see that these will both divide by 2, so I'm going to factor out a 2. If I pull the 2 out of this, I'm left with x squared. If I pull the 2 out of this, I'm left with 9, because remember, when I'm pulling the 2 out, or pulling any factor out, I'm actually dividing each term by whatever it is that they have in common. And the quick check is 2 times x squared is 2x squared, 2 times 9 is 18, so I factored out the greatest common factor correctly. Now I'd see that this is a difference of 2 perfect squares. That's x times x, that's 3 times 3. So I'm going to use my difference of perfect squares pattern. I take the square root of this one, put it here and here. The square root of this one, put it here and here. Plus, minus, and it's factored. Okay? That's factoring a difference of squares, first factoring out the greatest common factor that they both have in common. That's what greatest common factor means. Okay, I'm looking up here. I'm going to do the same thing if I can. These won't both divide by 18. They will both divide by 2. And that's the only thing I can see that they'll both divide by. So I'm going to pull a 2 out of these. Remember, when you pull it out, you're dividing the term by the factor that you're pulling out. I'm pulling out a 2. That will leave me with 18 divided by 2 is 9, v squared, minus 32 divided by 2 is 16. I pulled out this 2 because they both had a factor of 2 in them. That's the biggest number that they both had as a factor. That left me with a difference of 2 perfect squares. This is 3v times 3v. This is 4 times 4. So they're both perfect squares. A perfect square is what you get if you multiply something by itself. So I'm going to use the difference of squares pattern again. Open up 2 sets of parentheses. Take the square root of this one. That's the thing that you would multiply by itself to give you 9v squared, and that would be 3v. Take the square root of this one. Well, I would multiply 4 by itself to give me 16. Put that here and here. Make one positive, one negative, and we're factored. And there we go. We factored it completely. First we factored out the greatest common factor just because we saw that it had a common factor of 2. And then we looked and said, hey, that's a difference of 2 squares. Here's my 18v squared, my negative 32v squared. What's left here is 9v squared minus 16. Those are both perfect squares, and that's a difference. A difference means you're subtracting them. And since it fit the pattern difference of squares, I factored it in the difference of squares pattern. Square root of this one here and here, square root of this one here and here, make one positive, one negative, and don't let that factor of 2 that we factored out first disappear. It's still a factor. Okay? And that's what we're going to be doing today, factoring out greatest common factors whenever we run across them, and then factoring the resultant difference of squares. The student will factor a difference of squares, first factoring out the greatest common factor if necessary. Here's our pattern, and you've seen how to work them, so hopefully that made sense. If it doesn't, watch it again and maybe it will.